Swayam Prabha, free DTH channel for education.
Greetings. We will discuss another way of doing dense coding. And now you know what is dense coding, which is to send information about two classical bits using no more than a single qubit. That is stretching yourself beyond the Hollywood limit, not in violation of you're not disproving the Hollywood's theorem or anything like that, but you're using some additional resource to sort of beat the Hollywood limit. And now we are going to use 3 qubits. So there are like 3 cats in a state of being dead and alive, a superposition of being dead and being alive. And these are called as W states. And essentially, we will use the W states, the 3 qubit states, to beat the Hollywood limit, go beyond it, and demonstrate how dense coding can be done. So the original problem is still the same, that Alice has got a pair of 2 classical bits, and it can be any one of these 4 pairs, 0, 0, 0, 1, 1, 0, or 1, 1. And Alice can send only a single qubit to Bob. That is a constraint under which this information about 2 classical bits is to be communicated. But what we learned from Hollywood's theorem is that a single qubit cannot communicate information about any more than a single classical bit. The initial resource which is available to Alice and Bob is a state of 3 qubits which are entangled, and they are entangled. What it means is that they cannot be factored into tensor vectors of lower dimensions. All right. So this is a 3 qubit state, entangled state. And this is the first qubit. This is the second qubit. This is the third qubit. And the first qubit can be in a state either 1 or 0. The second can also be either in a state 0 or 1. The third can also be in a state 0 or 1. And there are these different possibilities that one can work with. You can have phase factors over here, and this is a general state that you write as a W state. This is named after Wolfgang Dur, or I don't know how to pronounce D-U-R with this 2 dots, 2 German dots on the letter U. But I think I could have found out there are resources available on the internet which tell you how to pronounce different words in different languages. But I'm sorry, I haven't done that. Well, let's just call him as Wolfgang. So Wolfgang came up with an analysis of these entangled 3 qubit systems, and it cannot be factored into direct product vectors of lower qubits. So that is a property that the entangled W states have. And we have the first qubit is with Alice, and the second and third qubit with Bob. And we take a particular case when n is equal to 1, gamma is 0, and delta is 0. And this is the W state of the 3 qubit vector which is with them. So this is the initial state. And The information to be communicated to Bob using no more than a single qubit is about 2 classical bits. And these 2 classical bits can be, they constitute a pair, but it can be any one of these 4 pairs. So Alice has got the first qubit. It remains entangled with qubit 2 and qubit 3. And Bob can now go away to a different location. With qubit number 2 and qubit number 3, Alice has got a single qubit, and she can do 1 qubit gate operations on her qubit. So she encodes information about these 2 classical bits by performing a gate operation on her qubit. And she uses a unitary transformation depending on which pair of 2 classical bits she has. So depending on that, she can carry out single gate operation on 1 qubit, and Bob now has got qubit number 2 and qubit number 3. And then Alice can communicate a single qubit. This is the one in which information about the 2 classical bits is coded, and she chooses an appropriate unitary transformation depending on which of these 4 pairs she has. So if she has the first pair, she leaves it alone so that the transformed 3 qubit W state is the same as the original one. If she has the second pair, she performs a NOT operation on her qubit, which is qubit number 1, but it remains entangled with qubit number 2 and qubit number 3. And then if she has third possibility, she performs the IY operation, and that impacts the W vector because it was originally in a state of 3 qubit entanglement in a W state. And if she has a fourth, she performs the poly Z operation on that. So these are the 4 possibilities, and depending on what she has done, she performs either the identity, in which case the original W state remains invariant. It remains 100 plus 010 plus root 2001. This is the choice that we made initially for the initial 3 qubit entangled state. If she begins with 2, then she does a NOT operation. So it is only on qubit number 1, which is with Alice, which is going to get inverted. So this 1 goes to 0, this 0 goes to 1, and this 0 goes to 1. The remaining states of qubit number 2 and qubit number 3 remain unchanged, and the transformed 3 qubit vector is this. If the pair of classical bits is 1, 0, then Alice performs the IY operation on the W 3 qubit vector. The IY changes this 1 to 0, but it changes this 0 to 1, but with a minus sign. There is a phase difference, you remember? And this 0 also goes to 1, but again picks up a minus sign. So you get a different 3 qubit vector. And if it is the fourth possibility, which is 1, 1, then Alice performs a Z operation, which is to change the south pole by a phase. So it becomes -1, 0 remains 0, this 0 remains 0, and this is the vector, 3 qubit vector, that the transformation results in. Okay, so the 4 vectors that you get, they are all orthogonal to each other, and Bob can now perform measurements on the 3 qubit system because Alice can send 1 qubit to Bob. So the qubit on which she has performed these operations, these different gate operations, and that is where she has coded the information. And that coded information is now communicated to Bob, and Bob can now carry out other gate operations on that and decode that. So that's the spirit which we have already discussed in the previous class. So I will not get into the details, but give you the essential idea that this dense coding can be achieved also using a 3-qubit entangled state. So there is some pre-shared entangled resource which is used. We have not violated the Holevoll bound, but within those limits, we have achieved dense coding. We have managed successfully to send information about 2 classical bits. And what has enabled this is not the refuting of the Holevoll's theorem. It remains intact, but we have used some additional resource, which is the initial 3-qubit entangled vector. So using that, dense coding has been achieved, and there have been various contributors to this thinking. So I will conclude our discussion by just giving you some references over here. And the work of Charles Henry Bennett and Stephen Weisner in 1992 is of great importance. This has been experimentally realized quite some time back, a quarter of a century ago. And they have used photons as qubits. In India, we have excellent work contributions from 2 distinguished quantum information scientists, Arun Pati and Aditi Sende at the Harishchandra Research Institute. And I would recommend that you go through their work in these papers. They have also worked with W states. And this whole information science is really now exploding because of the quantum bits. Because huge amount of information can be put into it. Means look at this amount of information. It goes as 2 to the power n plus 1 minus 2. And just 2 or 3 days ago, IBM announced the development of a 127 qubit quantum processor. So this is the amount of information that it can handle. You don't have access to the entire detail at one time, because if you access it, you're going to destroy the entanglement. The superposition will be lost. The moment there is any kind of interference, the system decoheres and the system collapses into eigenstate of the measurement. That's quantum mechanics. And you cannot access all of this information, but you can manipulate all of this information at one time by performing these multi-gate operations. So that is the advantage of using quantum bits. So like a 2-qubit vector, you can have a general vector written as a superposition of these different possibilities. And you can have a 3-qubit vector. So for 3-qubit vector, you have more possibilities. For n qubits, it goes as 2 to the power n plus 1 and minus 2. There can always, you can extract a phase factor and a overall normalization. So let's take the case of a 3-qubit vector. You already have some acquaintance with the 3-qubit states. We worked with the W states in this class. But a general 3-qubit vector can be written as a superposition of I, j, k, but each of these I and j and k can take 2 values, either 0 or 1. So there are this triple sum that you can carry out, and you can expand this triple sum term by term. So I have carried out the summation over k. So I take k equal to 0 and k equal to 1 over here. Now in the next step, I carry out the summation also over j. So j equal to 0 and j equal to 1 here. And in this case, j equal to 0 and j equal to 1 over here. And then I expand also over I. So I get a total of 8 vectors, and each has got a different coefficient, which is indexed by 3 indices. So alpha 0, 0 is the coefficient of this, alpha 1, 0, 0 is the coefficient of this vector, and so on. So there are 8 vectors in the superposition and 8 coefficients, which you can spell out carefully, write them together. And the probability of measuring the 3-qubit state in a particular ijk state is given by the modulus square of that coefficient. So this is how the 3-qubit states can be handled. There is an overall normalization, and one can extend this analysis to n qubits. And that is the reason there is so much competition between Google and IBM and Honeywell and so on to have a multi-qubit quantum computer. So this 127 qubit processor that IBM has just announced is a huge step in processing information, because it really goes as exponentially. It goes as 2 to the power n terms. So even if all of that information is not accessible at the same instant of time, because an observation would collapse the system into an eigenstate, you can process all of them together using multi-qubit quantum gates. And that is the advantage. And using this, a lot has already been achieved. For example, if you have 4 components in a 6-qubit system. So there are 6 qubits, first in the state 0, second in state 1, third in state 0, fourth in state 1, fifth in state 0, and sixth in state 0. But this is superposed with these 3 other possibilities. This is an overall normalized state. And suppose you're given this initially. You're given this initial superposition. And it is suggested that you should transform these into this superposition. This is a superposition of the same 6-qubit system, but there are 7 components: 1, 2, 3, 4, 5, 6, and 7. And you might think that, yes, I can do this using classical gates, because with classical gates, you can certainly manipulate the bits, zeros and ones, but you will need a certain number of steps if you were to use classical gates. In fact, you would need thousands of steps to achieve this, to go from this superposition to this superposition. You would need actually thousands of steps if you were to use classical gates and classical computing. On the other hand, using some tricks like the Deutsch algorithm told you that, okay, there is something that quantum entanglement can do, which classical computer cannot. And that is the supremacy of quantum computing, which is to be able to do what a classical computer cannot. And you can do this transformation from this combination of the 6-qubit system to this combination, which consists of these vectors, using quantum gates. And in one step, you can get this combination. In the second step, you get this. Of course, you have to use very smart quantum gates to be able to do that. And you can, that is what learning quantum computing is about. And then in the 4th step, you already get the final answer, for which classical computing or classical thinking, classical logic would have required like thousands of steps. So this is really amazing that you can achieve it in just a few steps. So this is the power of quantum computing. It is actually very difficult to execute because of decoherence. I told you that any measurement induces the system to collapse into an eigenstate. And this measurement can even be an inadvertent one, because any impurity can interact with any of the qubits in your apparatus and the system would decohere. So this is a great difficulty. The system is very fragile and interaction with the environment is dangerous, and the entanglement does not survive in these situations, which is why it takes a huge effort and a lot of money to make a quantum computer. So the physical implementation is extremely difficult. And these are some of the great ideas in recent times in developments in computer science. If you talk about some of the greatest ideas, they deal with creativity, abstraction, data information, algorithms, programming, internet, global impact. And these are the algorithms which actually run the world. We use the internet, public key cryptography, pattern recognition, data compression. So these are the important advances in computer science. Cryptography is of great relevance because of information security, and the RSA, named after Rivesh, Shamir, and Edelman, the RSA public asymmetric cryptography algorithms can be cracked. There have been these RSA challenges, and what enables this are algorithms such as the Shor's algorithm, in which you can factorize prime numbers and so on. So you can manipulate superpositions using quantum gates. You can do search algorithms, like if you have to find out that some of these switches are on and some are off, and you don't know which one is on and which one is off, and you have to find this out, then you can use things like the Grover algorithm. These were some of the earliest advances about a quarter of a century ago. And since then, quantum information science and quantum computing has come a very long way to achieve great things. And it all begins with this debate between Niels Bohr and Albert Einstein. And mind you, Einstein made huge contributions to quantum mechanics. He also challenged quantum mechanics. He looked for flaws, internal flaws in quantum mechanics. He looked for ways of restoring causality in quantum mechanics through hidden variables. And the debates between Bohr and Einstein they churned out a huge wealth of understanding of the laws of nature, which are quantum mechanical. Tests have been carried out. The Bell's inequality tells you how to test which logic works within which kind of limits. And this is where I conclude this class. I will refer you to some other articles, but of course there is a huge amount of literature which is available. It is being generated even as we speak, and there are advances. And my good wishes to all the students who are taking this course, that some of them will also contribute to this. So thank you all very much, and I will stop here for this class. Thank you and goodbye.